This session I said I'd show you the actual terms for your eigenfunctions, general eigenfunctions this time, that depend not only on the position, spatial position, r, but also on the two polar angles, so r, theta and phi. And from the previous session, these u's here, they're effectively a product of your big R that we've been solving, big R in terms of big F and so on. So you did quite a bit of analysis on what big R takes. And from earlier chapters on the Y, capital Y, Ln, the spherical harmonics. And this U effectively is just the product times a normalization factor, just to keep things normalized. But effectively U is just the product of the big R and the spherical harmonics, Y, capital Y, Ln. So convention here is so it's U of n, L, n. Okay? So for each of these three numbers here, just read n, L, n. So in this case, well, given which everything's different here. So in this case, n is 3, L is 1, and m is 0. Okay. Now, in earlier chapters, we talked about the so-called Bohr, B-O-H-R, Bohr radius. Okay. I wrote it as A0. I'm trying to remember the definition of the Bohr radius. I think it was the case, it was the distance from the nucleus in the hydrogen atom, I think, which had the distance at which the probability density was highest. And that distance was called Bohr radius, and it's labeled just A0. Right? So let's see, when L is 0, then m has to be 0. So in these two cases there should be no mention of thetas and phis, your y, your spherical harmonics. There won't be any dependence in this term of theta and phi. So they'll just be a function of r, and that's what you've got here, purely functions of r. And these terms here are from the normalization coefficient, which was a rather complex from previous session. It's the square root of, I won't even read it out, it's too tedious, but lots of factorials, cubes, and okay. So these terms come from plugging in the value of n and L into your normalization factor. Okay. Now here, for the first time of these three, we've got an L is 1, right, and the n is 0. So we have an angular momentum type term, and that explains where this comes from. So you got a theta here. So let's see. When L is 1, I think the spherical. I could check it if I can find it quickly. There was a list of the spherical harmonics in the textbook. If I can not take too much time finding the damn thing. If it takes too long, I'll skip it. So I think that y1 of 0 was cos theta. Anyway, something like that. All right. So here we have so n is 2, L is 1, and two cases for m. So m is +1 or -1. And we did the case when m is 0. That was this one. And now we get a theta phi term for the spherical harmonic, the y, big Y, capital Y, Lm, right? This term, which I think we've seen before. I think that was in the list we had in earlier chapters for y1, 1 or y1 minus 1. Okay, so if the plus 1 here corresponds, I guess, to the plus I here. Right? So that would be your y term, and this here would be your r term. That would be your big R. Alright, well things get a bit more complicated. Now again, and now here we've got n as 3, so like your third level, your third energy eigenfunction. Right? And L is 0, M is 0, so there'll be no mention of angles, theta and phi, no polar angles in your term. It'll all just be R, in terms of R. So this is getting, now here's where your Laguerre polynomials are starting to show themselves here, okay? And your normalization function, factor, right? Getting a bit more complex. Alright, now N is 3, L is 1 now, so expect some theta phi dependence, and here it is. So I guess this is the just my inspection must be the spherical harmonic for L equals 1, M equals 0. It's just cos theta. Okay. And again, you know, this term here with this, so this and this are your big R, right? Okay, so yeah, we could keep going, and if you care to, you know, if you're really into this stuff of trying to find the wave functions for the hydrogen atom, you could keep going. I mean, you haven't gone very far, but believe me, it gets more and more complicated, because then you have to calculate the Laguerre polynomials for higher and higher values of L and M. Or N and L. N and L. Okay. Alright. So now, well, here, there's a question. So we have these wave functions, and you know, to get probability densities, you